Alright, hell yes. We have mechanics of materials, and we're going to revisit this problem because I never solved it and got the right answer. You know, we got close, but hell yeah, we're going to actually get the official answer. So there's a couple aspects of this problem. What we're going to do is we're going to drop this thing onto a spring, or a string, I'm sorry, but anything in material mechanics, you can treat this as a spring. So as this drops, it's going to change in length. So this bar is going to be down here, and this spring is going to change in length. Now, the first aspect of this problem is it's like an impact loading. So if I had a bar that impacts onto something like this, what happens is that, heck yeah, this bar will change in length. And this bar can be modeled as a spring, and then the spring will change in length. So when we use energy, we say, hey, the potential energy up here is, let's say, mgh, and we're just saying this is h. But the total potential energy after the spring lengthens is actually plus this change in length. So if we wanted to equate the energy, the energy right here is just all potential. So we can say the potential energy, and then the energy at this point, it's all spring energy. You know what I mean? The velocity is 0, so there's no kinetic energy here. Velocity is 0 up here, no kinetic energy. So this is the point in the system that we want to analyze, and because this generates the max force, the max stress in the max change in length. You know what I mean? Once this stops, the spring gets to its lengthiest, and that's going to be the max force in the spring. And obviously this is a spring that has an area, and then so they want to know the max stress. So the first material mechanics equation is force divided by area, and then so heck yeah, that's going to be the max force. Okay, so the energy of a spring is 1/2 k change in length squared. And the potential energy will be mgh plus mg change in length. And the textbooks will write it like this. You have mg, but your height is h plus change in length. So that's kind of how the textbooks write it. But you should FOIL it out and say, heck yeah, you have your potential is both of these, and that's going to equal 1/2 k change in length squared. Okay, heck yeah. So now let's go back to our problem and see what we have for the initial setup. So when we bring this up to here, this is the string. The string goes taut. So right here is B. This is also L. And so let's just find this angle. If we found this angle theta, it would be, that's going to be the inverse tangent of B over L. Now, how do we know that? You know what I mean? It's because, heck yeah, the tangent of an angle is opposite over adjacent. And so here's the opposite, here's the adjacent. Cool. So that's going to be tangent. The angle is just inverse tangent of that B over L. Okay, hell yeah. And then we can just see, you know what I mean? Hey, what's this angle? Well, it's also theta. It's also B over L. It's also the inverse tangent of B over L. So this total angle right here is 2 theta. And what we want to know is what's the potential energy of this bar? You take the height of the center of mass. So we're just going to say, heck yeah, that's the height. And then when this bar gets down to here, you know what I mean? Here's the center of it. You know what I mean? So here's the center of it. And now we need to figure out like how much lower it went. Well, that's why I brought up this, because this is your common impact equation when your thing is just impacting in a very linear way. But here, this change in length isn't going to be, so this center of mass only does 1/2 change in length. So that's what I kind of wanted to show with that. Okay, so so for here, the potential energy was mgh plus change in length. For our equation, we're going to say potential energy is equal to the energy of the spring. So we're going to have we're going to have mgh plus 1/2 change in length. is equal to 1/2 k change in length squared. Alright, hell yeah. And so what we need to find h, so we're going to come in here and say that this hypotenuse is L divided by 2, and then here's our angle, it's 2 theta, and so the sun is shining on the sinin, so we have h is the hypotenuse times the sine of 2 theta. So sweet. And so we can put that in for here. So we're going to go mgh plus mg 1/2 change in length is equal to 1/2 k change in length squared. So now for this, you know, we can plug in, so there you go. So we can plug in h right there. What we don't know is this change in length, and maybe we don't even know k, but we're gonna find that out. So this is a material mechanics problem. So the first things that I do is write all the material mechanics equations. Strength is force over area. Strain is change in length over length. And then what relates, and then so here's what's going on, is like, let's say you have some sort of material and you can put a lot of pressure on it and see it like moves that much right there. But let's double the pressure, you know what I mean, then it moves like that much. It just moves twice as much when we double the pressure. So it's a linear relationship. And you know what I mean, we can measure this pressure change, you know, with one gauge, and then we can measure the change in length with like another gauge, you know what I mean? And so we know that there's a relationship there, and we know it's linear. We just want to know how it's linear. So we say strength is equal to modulus of elasticity. And you can just think strength is EE, but this really helps you out that this is the equation of a line, mx plus b, where your y-intercept is 0. See how this is, hey, y is equal to my slope times x. You know what I mean? So this is the thing that's constant. In an equation, this is the thing that's your constant. This doesn't change, but we can change these variables. And this is how you relate, you know, two dissimilar things. You know what I mean? Two things that have different units. You know what I mean? This has strength, this is in PSI, and this is a dimensionless unit. You know what I mean? It's dimensionless. You could also say we want to relate force by some sort of constant times, or I'm just going to use capital C, some sort of constant times change in length. You know what I mean? You could totally get an equation for that as well. And then you would have force in newtons is equal to change in length in meters. But hey, this constant would have to be it would have to be newtons divided by meters. You know, so then it would make sense. Okay, hell yeah. So once you get these three equations, then you want to substitute these into this equation. So we get F divided by A is E, change in length divided by length. And then I rearrange this. So I'm going to say F, I'm going to bring the A upstairs, is EA divided by L, change in length. This is the first one that I'm going to do because it's synonymous with the force of a spring equaling K change in length. So now I can say, hey, my K value is EA divided by L. And this would be a kind of a good one to kind of memorize for material mechanics purposes. Or like once you get it, just recall it. You know what I mean? Okay, cool. And then the other one that we can do, we can just solve for change in length. We can say change in length is FL, and then bring the E downstairs, FL over EA. Maybe that spells fleet. Okay, sweet. So, and then so right here, heck yeah, we want to throw in K, so let's do that. We're going to have 1/2, K is EA divided by L, and then change in length squared. Now, if you want to get the right answer to this, because I've messed this problem up so many times, it's really difficult not to make one tiny little error. But even just right here, this would be a good place to throw this into your calculator. So we're going to bring this over here. I'm going to get it negative 1/2 EA divided by L, change in length squared. And then I'm going to add it to this plus 1/2 mg change in length plus mgh is equal to 0. And then so my change in length is kind of my x term, and we have a quadratic here. So then what I would actually do I have alpha E stored in my calculator. This is 21. 2.1 times 10 to the 9 pascals, which is newtons per meter squared. That's the definition of a pascal. Area is 30 times 10 to the negative 6. That's turning this into meters, you know what I mean? Because there's, in 1 millimeter, there's 1,000. So if this is 1 meter by a meter, that's 1,000 millimeters by 1,000 millimeters. So there would be 10 to the 6 millimeters in a meter. Okay, hell yeah. And so you would just divide by 10 to the 6 to get meters. That's kind of the quick and dirty way. But anyway, we have that stored in our calculator as alpha A. And do we have anything else going on here? Oh, yeah, this is crazy. This is where you really have to throw some asterisks on the board. We know the material mechanics equations when we have like, hey, check out this. This is regarding this length. You know what I mean? So I have a material mechanics equation that says, hey, this is going to change in length, and this is the length of it. So this length is B, actually. You know what I mean? So we have to, and then we already just said, well, isn't our H in terms of the actual length of the bar? Sure, but these L's are not the same. So I'm not going to turn these into B's right here, but when I actually use them, I don't know how you, how you'd not mess that up. That's the easiest thing to mess up. Like, I would literally change this length into, there you go, L naught. So this will be very useful. If we say that's L naught, and none of these L's are L naught. Just the L that's into this H equation. This is L naught. So that's a pretty good way to not mix those up. Alright, hell yeah. So, let's solve this. So we can just, I think the easiest way to solve a quadratic without messing it up, especially with big and little numbers, is to do this. So we're going to have negative 0.5 alpha E, alpha A divided by alpha L, and then we have x squared. Okay, and then we're going to add 0.5. M is just 1, but we have alpha G, and then we have x. Cool, and then we got plus, M is just 1, but we have alpha G. And then I'm just going to put alpha H just so I don't mess it up. Alpha H in my calculator is 0.2, so let's solve for this one. L is 0.5, so we got 0.5 divided by 2 times the sine of 2 times inverse tangent of B divided by L is 0.25 divided by 0.5. Okay, heck yeah, so that's 0.2. Alright, so we have this equation, and we're just going to graph it. So we're just going to go zoom 6. And the change in length is always going to be a number definitely less than 1. So we can actually get our y minimum, or x, we're going to go from 0 to like 0.1. And there you go. So we can have it run, but we can find the 0 of this. Alright, let's get to 0. So we can find the 0 value, left bound, right bound, and booyah. So that's going to store it as x. So we're just going to come here. We have that. I'm going to store it as alpha d. So now we're just done with that. That's the easiest thing to do is just like, you know what I mean, get that and then start to move on with life. Okay, so then the other thing is we need to know, this is the way you can kind of do this in like, 3 different parts. Because maybe, like, I know that the force of a spring is K change in length. Cool. And that's going to be the max force. Well, didn't we just find the change in length? Cool. So I can find the max force. So let's do that. And this is just going to be EA divided by L. And then in my calculator, this is alpha D. So I have EA divided by L and then times alpha D. And I'm getting more used to not using parentheses. So in my calculator, this says E times L divided by L, but then it just goes on to the next term. So if I say multiplied by D, so this is not EA divided by L divided by D. You know what I mean? Okay, so I have that force max, and it's 707.7 newtons. Okay, so now it says what's the max stress in the cord. Well, then I can go here to my equation. Max stress is force max, divided by area. So I'm going to store this as alpha f, and then we have alpha f divided by alpha a. And, oh bummer, I don't know why I'm getting the wrong answer every time. Ah, shoot, I should really go back and actually solve this one through. Unless I can find my error pretty fast. Oh, hell yeah. Yep. No. I'm so glad I did this, because I don't know how you separate the fact that this B is the L that I'm using for these. I do not know how you separate that. But yeah, I just said force max was K change in length, and I just said that's EA divided by L. So this is wrong, because this has to be EA divided by B, or I guess just lowercase b, times D. So, and then B in my calculator is that length of that chord. I'm just glad I'm messing up and then catching errors, because I just don't know. You're going to lose your mind using the material mechanics equations with generic L, and then having something that's not even related to something changing in length. You know what I mean? It's going to drive you absolutely insane. So this is divided by B times D, and then so here's our force, 1,415 newtons. Store that as F, and so we can come back here, alpha F divided by A. Oh, I'm still horribly getting the wrong answers. So at some point, I probably yeah, right here. Holy Toledo. So yeah, right there. I said, yeah, all these L's were accounted for. No, they weren't. This L was not accounted for. So I'm gonna publish this video, because I can't do this. Yeah, I need a better system. Anytime that the thing that you're analyzing is changing length, and then your material mechanics equation just has the generic L, it's going to totally mess you up. So let's go back to here. This is 1/2 EA divided by alpha B. And I don't mind posting this video, because now we're going to graph this. What's our window? Yep, so we're going to graph that. We're going to get a new value of change in length that's actually correct. So we're going to go, got to go 0. So left bound, right bound. Okay, hell yeah. So we're going to, so X, we're going to store that as alpha D. All right, heck yeah. So so now we can find our, so we have alpha E, alpha A divided by alpha B times alpha D. So this is our force, 998.8 newtons. Holy Toledo. Store that as alpha F, and then we have alpha F divided by alpha A. And so this is your classic. Now, you're like, what is this number? Well, always just divide it by 10 to the 6. You know what I mean? Heck yeah. So that's going to be 3.3 times 10 to the 6 pascals, which is 33.3 times 10 to the 6 pascals, or 33.3 megapascals. And so that's the answer. Holy Toledo. But yeah, this problem, I totally forgot about it, you know what I mean? When I came back to it, I was just like, oh, easy peasy. And but you're like, hell no, because I'm just using generic material mechanics equations with this generic L term, and then with something else has that L term that's not changing in length, that's not having a force, that's going to mess me up every time. Alright, hell yeah. So I'm satisfied with this one. And I'm going to spend the rest of a little bit of today coming up with 2 other videos, maybe one and the same, but how to do this with pure letters. And, you know what I mean, and how to get the letters not mixed up. So, heck yeah. But this was just like, hey, how do you get the right answer fast? I would just solve for that change in length, and then realize that change in length is the spring equation, so you can get the force max. And then what the hell they asking? They're asking for stress, which is force max divided by area. I think anytime that you try to get like a, the answer just all in one big equation, ah man, it's a recipe for disaster. So I've always done things piecewise, and then they just make like a lot of sense. You know what I mean? They make more sense than trying to make it one big equation. Alright, so thanks for joining me on this one, and that's the video.